Okay, we're tackling this thermodynamics question. We are presented initially with some enthalpy change and entropy change data. We can see we've got some changes with silver chloride and silver fluoride, silver ions here, and some associated enthalpy data and entropy data here. And just as we look at this table, we notice that we've not been given this piece of information, and that here, this is very common, enthalpy data given in kilojoules per mole and entropy data given in joules per Kelvin per mole, and that difference between kilojoules and joules will be relevant later on when we come to calculate the feasibility of reactions. But for now, we're just working with enthalpy in the first couple of questions, and first up they want us to define the term enthalpy of hydration of an ion. And this is one where we want to just have the definition memorized along with a few other enthalpy definitions. So we'll say that the enthalpy of hydration is the enthalpy change. We can just write delta H for when 1 mole of a gaseous ion forms aqueous ions. Okay, on to some calculations. So the next part of the question says for it to use data from the table to calculate a value for the enthalpy of hydration of the chloride ion. So going back to our definition, that's when 1 mole of gaseous chloride ions form aqueous chloride ions. So we're interested in going from Cl minus gaseous to Cl minus aqueous. That's the move that we're interested in here. Now we obviously don't have the data for that, but we do have the data for silver chloride going to silver and chloride ions gaseous. We have the data for silver chloride dissolving and becoming aqueous, and we have data here for silver ions becoming aqueous. This silver fluoride data is not going to be relevant to this question. So we're going to draw a cycle now to help us work out what to do, to help us work out the answer. We'll start with silver chloride at the bottom. Solid silver chloride, that's going to be the lowest energy state of the different things we've got here. And that silver chloride can undergo a couple of different changes. We can see here that we've got the enthalpy of lattice dissociation. That's when the solid silver chloride goes to gaseous silver and chloride ions. That's going to be the highest energy option. So we'll put those right up here. Ag plus gaseous and Cl minus gaseous. Okay, this is called the enthalpy of lattice dissociation. Okay, it's the opposite of the lattice enthalpy of formation. So we're not forming the lattice, we're dissociating the lattice. So we're going up here, and that's again we can see up here of plus 905. These are all in kilojoules per mole, these values, so I won't write down all the units each time. That's one thing we can do with silver chloride. The other thing we can do with silver chloride is go to the aqueous ions. So we can just dissolve that in solution into solution like this. Okay. Now we are interested in this change. Chloride, gaseous chloride ions going to aqueous chloride ions. That means we're interested in the change from this to this. But between here and here, another thing is happening as well. The gaseous silver ions are forming aqueous silver ions. So let's draw that change in first, where we're just changing the silver ions. Okay, so we'll change the silver ions to Ag plus aqueous, but we won't change the chloride ions. We'll leave those alone, Cl minus gaseous. Okay, and we know about that change because we actually have it here. There's that change, so we can write in minus 464 there. And I see that I forgot to write in the number here for dissolving the silver chloride. We can pick that out of the table here as well. So we've got plus 77 there. And so what we're left with is this change is described by this arrow here. Okay, so this arrow describes the enthalpy of hydration of chloride, gaseous chloride ions, or of chlorine. Right, hopefully when you've got a table written out all like this, when you can see the cycle like this, you can see that we're interested in the value of this number. It's going to be negative because we're going down, and it's just going to be the difference between this and these values. So we can do our calculation just by doing 905 minus 464 minus 77. Okay. And that, if we put that in our calculator, should give us minus 364. And then we don't forget to copy the units from up top of the table here, kilojoules per mole. Kilojoules per mole. Okay. On to the next part. And it asks us to suggest why the hydration of the chloride ion is an exothermic process. Well, energy is given out when bonds are formed, when strong forces of attraction exist between particles. So we're wondering to ourselves, what could it be when the chloride ion is dissolved in water? What strong forces of attraction might form? And we think of the chloride ion and we think, right, that's Cl minus. And we think of the water molecule and we think, what have we got? We've got HOH with a strong delta plus, delta minus, delta plus. We've got those lone pairs on the water, on the oxygen atom. Where might a strong force of attraction form? Well, if this delta positive hydrogen, this slightly positive hydrogen, would experience electrostatic interaction, electrostatic attraction to the chloride ion, and so we can just write that out. The diagram will help, but if we're going to write it out in words as well to make sure we pick up all the marks, we can say water is polar. Right, that's just describing this delta minus delta plus bond that arises from oxygen's high electronegativity. Water is polar, and there is a force of attraction between the delta positive hydrogen in water and the chloride ion. Okay. On to the next part, part D, and we're told that silver chloride is insoluble in water at room temperature. And it says use data from the table to calculate the temperature at which the dissolving of silver chloride in water becomes feasible. So we're interested in the point at which something becomes feasible. As soon as we're talking about feasible or spontaneous, we're thinking of our Gibbs free energy equation. So we're going to just write that down. Delta G equals delta H minus T delta S. We need to have that memorized and able to use that. And we can see we've got delta H information here and delta S information here. We're interested in the dissolving of silver chloride. Let's see if we've got some information about that in the table. Yeah, here's silver chloride dissolving. Here's a delta H value. Here's a delta S value. And we're interested in the temperature at which the dissolving becomes feasible, at which it is just feasible. Well, that's the value when delta G is 0. So we'll put in 0 equals, and then for delta H, we can put in plus 77. Now, we'll do everything in joules. This is in kilojoules, so 77,000 joules per mole, minus T times delta S, 33 joules per Kelvin per mole. Okay. We can rearrange this, add this to both sides. It's probably the easiest thing to do. So we get 33 T equals 77,000, and we'll divide both sides by 33 and see that T is going to be 77,000 divided by 33. Stick that in our calculator and get an answer of 2,333. And remember, the units for temperature when you're doing these calculations are Kelvin. Okay, and then it asks us about the significance of this temperature value. What might we conclude from this temperature value for how hot the water needs to be in order for silver chloride to dissolve in it? Well, this value is way above the boiling temperature of water. So at this temperature, water is not going to be water anymore, it's going to be steam. So we would say something like above boiling point of water. So water would evaporate. Okay. Last part. When silver fluoride, and note the change now, we're not dealing with chloride anymore, we're dealing with silver fluoride, dissolves in water at 25 degrees C. The free energy change is -9 kilojoules per mole. Just pay attention to the units in these calculations every time. Use the information from the table, this information and data from the table to calculate a value with units for the entropy change when silver fluoride dissolves. So this is this value here, this entropy change value that we weren't given, that we're supposed to be calculating. We're just going to use our Gibbs free energy equation again, delta G. Always write it out before you start manipulating it. We're going to have to move it around for this problem, but we always write it out like this first. This time, it's not T that's the unknown, it's delta S that's the unknown. We've been given G, -9, and I think it is easiest just to go in joules every time, so -9,000 joules per mole equals delta H. We've got that here, -15,000 joules per mole minus T delta S. Now actually for T we've been given 25 degrees C. Remember we need to use Kelvin, so we're going to convert that 25 degrees C into Kelvin to get 298 Kelvin times delta S. We just need to rearrange this to get delta S as the subject and solve for that. What should we do? Let's add 9,000 to both sides, and if you can manage at the same time, add this to both sides. So on the left we're going to get 298 delta S equals, now we've added 9,000 here, so we're going to get -6,000 there, and then we can divide by 298 delta S equals -6,000 divided by 298, and we're going to get about -20 joules per Kelvin per mole.